We continue with our discussion of formal epsilon delta proofs, and the real value of this definition is that it allows us to establish the mathematical truth of the um, limit rules that we have been using from before. So, for example, so first let me recall the definition of limit. Limit is x goes to x naught of f of x equals L if for every epsilon greater than 0, there exists a delta dependent upon epsilon greater than 0, such that x within x naught, x within delta of x naught implies that f of x is within epsilon of L. Okay, now in these proofs, the triangle equality comes up a lot. So uh, this says that for two real numbers, any two real numbers a and b, it is true that a plus absolute value of a plus b, or the absolute value of a minus b, is less than or equal to the absolute value of a plus the absolute value of b. Okay. Now we're going to use that to prove this. We had this rule already, and we accepted it on authority or because it appealed to our intuition. That the limit, if the limit of f of x at x naught is L, and the limit of g of x at x naught is m, then the limit of the new function f plus g at x naught is equal to L plus m. The limit of a sum of functions is the sum of the individual limits, provided that the individual limits exist. Okay? So now we give a formal proof of this. When you said that the limit as x goes to x naught of f of x equals L, what you meant formally was that for every epsilon greater than 0, there is a delta sub f such that x within delta sub f of x naught implies that f of x is within epsilon over 2 of L. Okay, so two things I'll point out here. One is that we're talking about functions f and g, and the delta for the f for the function f and the delta for the function g might be different. So that's why I'm going to use delta f for the f function, and delta g is the delta associated with the g function. The other thing is that the epsilon, we have to be able to make um, the difference between f of x and L less than any arbitrary number. So the arbitrary number here I'm choosing is epsilon over 2. Epsilon over 2 here is a convenience. You'll see how it works out with the algebra later, right? I could have said for every epsilon over 2 greater than 0, there's a delta f such that, and so on. Okay. All right. Similarly, when you said that the limit as x goes to x naught of g of x is m, what you meant formally was that for every epsilon greater than 0, there is a delta g such that x within delta g of x naught, but not equal to x naught, implies that g of x is within epsilon over 2 of m. Now we need to consider if we can um, x close enough to x naught, then can we get f plus g arbitrarily close to L plus m? Okay, so we need a delta. So I'm going to take the delta as the minimum of delta f and delta g. Okay, so if a delta works for any limit, if a delta works, then something smaller than that delta also works. Okay, so I wanted delta, which would be smaller than or equal to, whether we're talking about delta f or delta g, it's going to be less than or equal to that. So I take delta to be the minimum of delta f and delta g at any point. Okay, then 0, if x is not equal to x naught, and it's smaller than that delta, then let's consider the difference between f plus g of x minus L plus n. Well, that's f of x plus g of x minus L plus n by the definition of a sum of functions. Now, you see I have an f of x minus L in there, and I have a g of x minus m. And those are things that I know about. I already know that those can be made small. So I separate them out, and then I use the triangular inequality. And so that is less than or equal to absolute of f of x minus L plus absolute of g of x minus m. Okay. Now, if x minus x, absolute x minus x naught is less than delta, and delta is less than or equal to delta f, then I know that absolute value of f of x minus L is less than epsilon over 2. That was the assumption that we already had before, that the limit exists and it's equal to L. Okay. Also, if absolute value of x minus x naught is less than delta, and delta is less than or equal to delta g, then absolute value of g of x minus m is less than epsilon over 2. So both of these, absolute value of f of x minus L is less than epsilon over 2, and absolute value of g of x minus m is less than epsilon over 2. Okay, and if I add the epsilon over 2 plus epsilon over 2, that's equal to epsilon. So there exists such a delta that if x is not equal to x naught, and it's within delta of x naught, then the value f plus g of x is within epsilon of the value L plus m. Okay. Now, for the limit of a difference of functions, I claim that if you use the triangle inequality again, you can get the same thing. You should be able to almost copy the previous proof to get the rule for the limit of a difference of functions. Okay, the scalar multiple of a function. If the limit is x goes to x naught of f of x equals L, we saw the rule that, and c is not equal to a real number, c not equal to 0 is a real number, then the limit is x goes to x naught of c f of x is equal to c times L. Okay, so we already had this rule. Now let's get a formal epsilon delta proof. And then we know that this rule is in fact mathematically true, and we're not just appealing to our own intuition. Okay. So, given that the limit as x goes to x naught of f of x is equal to L, that means that for every epsilon greater than 0, there is a delta such that when x is not equal to x naught, and x is within delta of x naught, then f of x is within epsilon over absolute value of c of the limit L. That's what it means for that limit to be equal to L. Okay? So that's been given to us. When we claimed that there was this limit, then we were saying this mathematically. Okay? Then, x not equal to x naught, and within delta of x naught, implies that now I'm interested in the difference between Cf of x and Co. The absolute value of that difference is equal to C times f of x minus Co by the definition of multiplying a function by a scalar. Now I can take out the absolute value of C from the absolute value signs, right? And now I have the term absolute f of x minus L. But I know that when x is within delta of x naught, that absolute value of f of x minus L is less than epsilon over absolute value of c. So this thing here is less than absolute value of c times epsilon divided by the absolute value of c. So this is equal to epsilon. Okay. Okay. The limit of a monomial function, well, we already did this, I think. So I'll see to prove that again. But we can now use these rules. We can trust these rules that we develop. So I can say limit as x goes to x naught of ax plus b. Okay. The limit of a sum is the sum of the limits, so I break that up. Now it's limit of ax plus the limit of the constant function is b. And then I can pull the a out of the limit sign because that's the limit of a scalar multiple of a function. And I've already proven the value that x goes to x naught, right? So all of these rules that we've been using, and we've already been using before this, they have now been proven mathematically that we're allowed to use them. These are mathematically true. Okay, so we can trust these rules. And having established a proof of these rules, then we don't have to go back all the way and do a formal epsilon delta proof. Okay. We also had the rule for the limit of a product. So if the limit at x naught of f of x equals L, and the limit at x naught of g of x is equal to m, then the limit at x naught of the new function f times g is equal to L times m. The limit of a product is equal to the product of the limits, provided that the individual limits are known to exist. Okay, how do we know that that's true? Well, okay, so this is the algebraic manipulation. I need to consider f of x times g of x minus Lm. Okay. Now I don't know any. I know something about f of x minus L. I know something about g of x minus m. I know that those can be made arbitrarily small. Okay. I can let delta equal the minimum of delta f and delta g, and so when x is within delta of x naught, then f of x minus L can be made less than something, and g of x minus m can be made less than, the absolute value of g of x minus m can be made less than something. So what I would do is I subtract off from the term on the left, I can subtract off an LG, and I can add an LG. And if I do that, then I can factor that to get f of x minus L times g of x plus L times g of x minus m. And that's really the essence of the proof. I mean, the rest of the proof can be read, but I wanted to tell you why that was being done. It's so that you can get terms like f of x minus L and g of x minus m in your workings. Okay. So again, the reciprocal of a function. Um, the proof is in your text or in some text, anyways. If the limit as x goes to x naught of f of x is equal to L, then the limit as x goes to x naught of 1 over f of x is equal to 1 over L. So what are you going to need to do? You're going to need to consider the difference between 1 over f of x minus 1 over L. And you don't know what that is. You don't really, we haven't told you really anything about f, right? What we have told you is that the limit is L. As x gets very close to x naught, then f of x gets very close to L. So we know that we can make absolute value of f of x minus L very small. So what you would need to do is to consider that absolute value of 1 over f of x minus 1 over L. In order to get something like f of x minus L, I can cross multiply and put over a common denominator. So that's the absolute value of f of x minus L over the absolute value of f of x L. And this term, absolute value of f of x minus L, can be made arbitrarily small. Okay, and that's the essence of the proof. You can read the rest for yourself, but I wanted to point that part out to you. Okay, limit of a quotient of functions. Now the thing is that I don't have to do a lot of work for this one, because I've already done the heavy lifting in the proofs that I had before. Right, so let me remind you of this rule. If the limit as x goes to x naught of f of x is L, and the limit as x goes to x naught of g of x is m, and m is not equal to 0, then the limit as x goes to x naught of the quotient f of g at x is equal to L over m. The limit of the quotient is equal to the quotient of the limits, provided that the individual limits exist and the denominator m is not equal to 0. Okay, and then instead of, if we want to prove this formally, instead of going all the way back to the epsilon delta definition, we could say, well, I've proven the rule for the product, and I've proven the rule for reciprocals. So let me think about it this way. The limit as x goes to x naught of f of x over g of x is the limit of f times the limit of 1 over g, right? Because this is the limit of a product. We've already proven that with the epsilon delta business. Okay, so then that's equal to L times the limit of 1 over g, and that's L times 1 over m, which is equal to L over m. Okay, so the idea is you use an epsilon delta proof to prove the very basic rules, and then you can use those rules to prove more rules, perhaps without going back to the epsilon delta definition. Okay, composition of continuous functions, and so if you have the composition of f of g of x, okay, so the limit as x goes to x naught of g of x is m, and the limit as y goes to m of f of y is f of m, so f is continuous at m. And then, because f is continuous at m, you can pull in the limit inside the argument of f. Okay, so that was the rule that we had, and I have put the discussion in the notes for you. It's a bit advanced perhaps for this course, but it's there if you want to read it. Okay, and we go on with a bit more of formal limits in the next lecture.